Atoms are almost entirely empty space. If an atom were enlarged to the size of a classroom, the nucleus would be no bigger than a pinhead. Yet that tiny core holds over 99.9% of the atom's total mass. When we plunge past the distant electrons, we find a tightly packed cluster of protons and neutrons. These are nucleons, the foundational building blocks of matter. The nucleus is an extreme environment, concentrating nearly all the mass of the universe into an impossibly small volume. Basic arithmetic suggests a simple rule. The total mass of an object must perfectly equal the sum of its individual parts. Let's apply this to an oxygen-16 nucleus. It contains exactly 8 protons and 8 neutrons. Based on their precise individual weights, we expect a total mass of 16.127 units. However, when we measure the actual assembled oxygen-16 nucleus, the experimental mass is only 15.990 units. The nucleus is lighter than its own ingredients by 0.136 mass units. This discrepancy is a consistent physical reality, not a result of rounding or measurement error. When free particles assemble into a nucleus, a fraction of their mass disappears, breaking the most basic rules of addition. Physical matter cannot simply cease to exist. If mass goes missing, it has to transform. Albert Einstein solved this puzzle when he discovered that mass and energy are inextricably linked. His equation, E equals mc squared, treats mass and energy as two forms of the exact same cosmic currency. They are exchangeable at a rate defined by the speed of light squared. Within this framework, the universe allows matter to be spent to purchase immense amounts of energy. We can map this rule directly to our oxygen nucleus. That specific chunk of missing matter is the mass defect. The formula for mass defect is simple. We subtract the actual mass of the assembled nucleus from the combined mass of its free protons and neutrons. The moment these particles lock together, that mass defect is converted into pure energy. This is binding energy. It is the powerful glue required to hold the core together, overcoming the natural electrical repulsion between protons. A nucleus is lighter than its parts because it sacrificed a piece of its own mass to pay the cost of its own stability. Because mass turned into energy to bind the nucleus, you would have to supply that exact amount of energy back to the system to break it apart again. The metric for stability is binding energy per nucleon. The higher this number, the more tightly the nucleus is held together. This chart plots binding energy per nucleon for different elements. It is practically constant for middle mass elements, but drops for very light or heavy atoms. The curve peaks at iron 56. At 8.75 MeV, it's among the most stable states of matter. Consequently, the universe favors intermediate mass atoms as the most stable configuration for nuclear matter. Because the c² multiplier is so vast, manipulating this missing mass releases 1,000,000 times more energy than any chemical reaction. Breaking heavy, unstable nuclei into lighter ones, a process called fission, is what powers our modern electrical grids. Fusing light nuclei into heavier ones is the mechanism that fuels the stars. This tiny missing fraction of atomic mass ultimately serves as the foundational power source for the entire universe.